framework of the Unificare Initiative, a program sponsored by the Fondazione Ente Cassa di Risparmio di Firenze to foster dialogue and promote interactions between researchers and the general public in the occasion of the celebrations for the 100th anniversary from the foundation of the University of Florence. Professor Steinhardt is best known for his development of new theories of the origin, evolution, and future of our universe. He co-authored seminal papers on the foundation of the inflationary cosmology. He also became a leading developer of a new class of cosmological model that replaced the so-called Big Bang with a big bounce, a sort of a smooth transition from contraction to a dense, hot universe that keeps on expanding and cooling. On Thursday in San Marco, he will deliver a lecture on this topic, so you are all invited to come and listen to Paul on that occasion. Paul has also made significant contribution researching the dark side of the universe, dark energy, the cosmological constant problem, and dark matter. In particular, he introduced the concept of quintessence, a form of dark matter, that dark energy that changes over time, as opposed to the cosmological constant, which is by definition constant and static. But then Paul Steinhardt is also well known for investigating a new form of matter that we know that we call quasi-crystals. Quasi-crystals were thought to exist only as man-made materials until he co-discovered, together with our friend and colleague Luca Bindi, who's sitting in the audience, the first known natural quasi-crystal in a sample displayed at the Museum of Natural History in Florence. Together with Luca, he led an adventurous expedition to trace back the origin of the small specimen in the wilds of the Far Eastern Russia. And today he will address this discovery in this today's lecture. He received a lot of awards for his distinguished career, the Dirac Medal in 2002 for his works on the inflationary model of the universe, the John Scott Awards for his work on quasi-crystals. He also co-chaired with Luca Bindi the Aspen Institute Award for scientific research in collaboration between Italy and the United States, the Niels Bohr Institute Medal of Honor, and so on and so forth. So again, it's really a pleasure and an honor to welcome you here at the Department of Physics and Astronomy. So the stage here. Una cosa rapidissima, la dico in italiano per gli studenti. Abbiamo un QR code che ora verrà anche proiettato, potete inquadrarlo e per certificare la vostra presenza all'evento di oggi in caso appunto vogliate richiedere i crediti formativi. Ok? Grazie mille, ringrazio anche, colgo l'occasione per ringraziare Germana per l'occasione dell'evento e veramente grazie mille per tutto il tuo lavoro.
So if you want to register for this lesson, otherwise we have also here in paper, in case you miss this one. Okay. And then it is difficult for me to close this without saying it. And come si chiama? Germana, you want to say something about this or just for showing? Okay, so in case, okay, here is Professor Steinhardt. Okay, so now I shall start the presentation and turn. Okay, you should see. Okay, so if you want to say there, okay, just for having some. Huh? Okay.
Now this microphone's on. Can people hear me in the back?
Maybe this one. No, this one is too much. Like this.
Perfect.
Okay. Io sono la distanza di controllo dell'energia.
Thank you, Professor Finelli. Thank you, Caffè-Scienza, for inviting me here. It's a great honor and a pleasure to be here, to be talking to you about this subject, because an important part of the story takes place right here in Firenze, involving not just me, but hero Luca Bindi, who is, but as you'll see, plays a central role in the story. It's been a great friend since this story began, and partner, and it's a real pleasure to be here and to honor him and to honor the work that we've been doing. So the story is going to be about things that are impossible. The word impossible occurs many times during this story. In this sense, it's a little bit like a fairy tale, a scientific fairy tale. I hope it's a true scientific fairy tale. I try to stick to the truth. But nevertheless, it gives that impression because it's so different than a normal scientific project or scientific experiment or series of experiments. So like any good fairy tale, it should involve some things that just seem bizarrely unlikely to occur. And there'll be barriers that stand in the way at various points. And there'll be some magical thing that happens at various points to overcome that barrier. And also, like a good fairy tale, there's not just the main theme of the story, but there's some interesting side branches to the story that add color to it. So the story involves things beyond usual science. It involves things like secret diaries will be playing an important role. There'll be a search for a missing Dutchman. There'll be a mysterious Romanian. There'll be smugglers, KGB agents, cannons, atom bombs, and last but not least, bears. And at various points, you'll probably ask yourselves, were these guys crazy to be continuing this story when there's so many barriers in the way? And the best way I can address that question right up front is to say, imagine someday you have the chance in your lifetime to work on a project which has secret diaries, mysterious Romanians, atom bombs, and bears. Grab onto that story, just take it wherever it leads you. And that sort of was our attitude. Various points where we would stop, it was just, so what? We just stick with it and go forward and see where things take us. Unfortunately, they worked out in a favorable way. But that wasn't obvious. You should imagine that you know the end of the story, most of you, but you have to imagine as you're going through the story, you don't know how it's going to end. The story could end at any point due to some surprise, an unfortunate surprise. So we begin with the beginning of the story, which begins actually in the 1980s, which is the first time the term impossible comes into play, because the subject we're going to be talking about, this form of matter, quasi-crystals, was itself believed to be impossible. Not just sort of impossible, but mathematically proven rigorously to be impossible, using rigorous mathematics developed in the 19th century. So not just a recent idea, but an idea that was taught in textbooks, including textbooks I learned from. In the opening pages, certain things are impossible, and one of the things that's impossible is to have a material that diffracts electrons like a crystal. When you send electrons to it, produces a diffraction pattern of point-like spots, which is a sign of a high degree of order in a material, a high degree of atomic order in a material. So it gives spots like that, but with a symmetry that is known, rigorously shown to be impossible for crystals. This was the content of a paper that appeared in 1984 with Dan Shechtman, Ilan Blech, Jimmy Gradius, and John Kahn, in which they had found accidentally this material, this aluminum mixture of aluminum and manganese, aluminum-6 manganese material, that produced these feathery-looking, disordered-looking grains, except when you shone electrons through them, formed this beautiful point-like, crystal-like pattern, except that the pattern is full of pentagons, if you look at it. And in fact, it has these rings of 10 spots, which these rings indicate that you're looking down an axis with either 5-fold or 10-fold symmetry. And both those symmetries were known to be impossible for crystals, thought to be impossible for any form of matter. That's what we used to learn in the early days, in the pre-1980 days, when you learned about possible forms of matter. So let's just remind ourselves what crystals are. Crystals are materials with an orderly arrangement of atoms, in which the atoms form either as a single unit, or as a group of units, or as a group of molecules. They form some sort of cluster that repeats over and over again with equal spacing along any single direction to form the structure. So it's a little bit like a tiling in 2 dimensions. So let's imagine you're giving you have a job that you want to replace your shower floor with some kind of tiling, and you like it to have some kind of orderly pattern to it. And you want it to be a crystal, a periodic pattern. So periodic means the same as crystal. And you want to have a periodic pattern. What kind of patterns can you make? Well, if you want the tiles to be identical, you could make them in squares. Obviously, many of you have seen square patterns before. And this pattern not only is made of squares, but the pattern it makes has a square symmetry. So it's not just true when I rotate one tile by 90 degrees, I get back the same, something that looks identical. If I take the entire tile pattern and rotate it by 90 degrees, it looks like it has the same pattern. And then you might think, okay, what other things can you make? Well, you could make things with triangles. You could tile your floor with rectangles, with parallelograms, and rhombuses, and hexagons. And you can imagine the list goes on and on and on. But it doesn't. That's the end of the list. That's the only symmetries that you're allowed to have. Everything patterned you've probably seen in your lives, except for maybe one or two, a few of you, has been a pattern when it involves in some sort of decoration of one of this small subset of patterns. Because until fairly recently, those were the only orderly patterns that humans knew. In particular, if you were to try to tile your bathroom floor with pentagons, woe to you, because pentagons won't fill the floor. They're going to leave those spaces in there. So that would be unfortunate. And the same would be true if you decided to choose heptagons, regular 7-fold tiles, or 11agons, or 153,417 agons. In other words, there's an infinite number of symmetries which are forbidden, and a small, countable number of symmetries which are allowed. When you go to 3 dimensions, you have a little bit more freedom because you can choose different symmetries along different directions. So there's a greater variety, but it's simply a play on what I've just shown you in the 2-dimensional case. It's just those restrictions are made for any single direction. So for example, if you tried to make a material with the symmetry of a football, I can say football here in Europe. The pentagons, if you follow them, are along axes of 5-fold symmetry. And you know, from what I just showed you, that you can't have 5-fold symmetry along any direction in a periodic pattern. A football has the same symmetry of a geometric figure known as the icosahedron, 20-faced figure made of triangles. It's one of the Platonic solids. And this is impossible 6 times over because this has 6 independent 5-fold symmetry axes in it, which is as many as you can pack into 3 dimensions. So, when I began to read about materials, first, one of the early pages had a picture like this and said, this is absolutely impossible, you've never seen a material like this. And yet, that material that Sheckman et al. Were reporting, when they rotated at various angles, appeared to have just exactly this symmetry. So what was going on? Well, actually at the time, there already existed a possible explanation for this idea. It just wasn't well known at the time. And this was an idea that I was developing with my student at the time, in those days, Del Levine, and now a professor at the Technion, in which we were trying to see if we could violate the rules of crystallography and find some way to create patterns that are supposed to be forbidden. In particular, we were interested in going after that icosahedral case, because that was the most forbidden case. So if you're going to try to do something new in science, in great convention, one way to go about it is to ask yourself, what are the assumptions that people have been making that led to the present conventional idea? And can you come up with any imaginative idea to break one or more of those assumptions? Because if you can, maybe you found a path to unlock a path to a new idea that breaks convention. In this case, the basic assumption that was being made was that the only orderly arrangement you can make of atoms is a periodic pattern, one which just repeats in the most boring way, one unit after a time, repeating with equal spacing. Another mathematical possibility, though, is to produce a pattern which is so-called quasi-periodic. And quasi-periodic doesn't mean just sort of periodic. It means something very specific. It means instead of being described by a single repeating function, you're described by two, or it could be three, or a finite number of repeating functions, where the repeating length, the repeating frequencies have a ratio which is an irrational number. So in periodic systems, you only have a single period needed to describe the entire system. And if you were trying to introduce two periods, they would have to have a rational ratio for a crystal. But now we're asking what happens if you allow the possibility that you have, let's say, two different kinds of repeating units, one repeating with one frequency and one repeating with another frequency, with a ratio of the periods as an irrational number, a kind of disharmony in space, much like if you were to make two sounds or tones whose frequencies were relatively irrational. You might interpret it as noise, but it's actually not noise because you take its Fourier transform and you take its frequency spectrum. It's actually two frequencies whose ratios are irrational, having a rational ratio. So what happens if you take the sound idea and move it to space? Well, then it turns out you can make new kinds of structures, which we call the quasi-crystals. And the quasi-crystals, like crystals, can have rotational symmetries. But in fact, they can have rotational symmetries which are impossible for crystals. In fact, they can have all the rotational symmetries that are impossible for crystals. So by relaxing the condition from periodic to quasi-periodic, you open up an infinite number of new possibilities that people hadn't considered before. In particular, you can produce patterns with five-fold symmetry in 2 dimensions and icosahedral symmetry in 3 dimensions. Now, our inspiration for this idea came from a study of this particular tiling, and it's known as a Penrose tiling. I just want to ask, raise your hand if you've not seen a Penrose tiling before. Everyone has seen a Penrose tiling before. Okay. Well, if you haven't seen one before, or even if you have, you might stare at this pattern and ask yourself, if I showed you this pattern and then asked you to continue the pattern, do you know how to do it? To maintain its perfect quasi-periodicity. Well, you might say, yeah, I can see some repeating elements in there, like those 5 stars, 5 rhombuses around the center which form a star. And then you say, I see another one, oh, but it's rotated. But here's one that's similar. And then if you try to work it out, I think you'll find that every time you think you have the rule, you don't. The rule breaks. If you could find a rule, you would have found a 5-fold symmetric periodic pattern which violates the laws of mathematics and crystallography. So you would have found something truly impossible. This is possible, it's right there before your eyes. So how do you see what's going on here? Actually, when we came across the Penrose tiling, the only thing that was advertised about it, beginning with its creator, Sir Roger Penrose, and even since then, was that it was non-periodic. So we knew what it wasn't, but we didn't know what it was. So to determine what it was, we began to investigate it, and it turns out to be useful if you were to say, take those tiles, pull them out, and then label each of them with those line segments, just as shown on the right. Then you make a rule that I'm allowed to join 2 tiles together, but only if those lines go continuously along the interface. That's important, because if I just give you the tile shapes alone, I can take those tiles and I can make a periodic pattern with one of them, either one of them, or a combination of them. But if I impose this rule, It turns out that forces a pattern to be non-periodic. That was Penrose's goal, to find a pattern, rules for putting it together such that you could force it to be non-periodic out to infinity. It was thought to be impossible until in the early 1950s. It was believed, mathematicians thought they had proven rigorously that you could not have such a pattern. It turned out the proof depended upon an unproven lemma, which turned out to be unprovable, that's to say, wrong. And that led to the discovery of the first example of a forcible non-periodic pattern. It involved something like 20,000 different tile shapes. And then over the years, that number got decreased. Penrose's contribution was to reduce that to just 2. And some of you may know that in the last year, another group of mathematicians have even reduced it to 1. So our view of what was impossible has become possible mathematically. In this case, if we put the tiles together now in this pattern, now with these line segments, it now reveals something about the structure that you couldn't have guessed. If you looked at the structure and you thought it was disordered, if you had that impression, this corrects that impression. Because when you put the tiles together, they form these continuous lines that run throughout the structure. So there actually is an order. When I put a tile on the right, it actually is forcing some conditions arbitrarily far out to the left and arbitrarily far out to the right. Now the question is, what kind of order does this have? Well, first of all, you'll find that there's these 5 sets of parallel lines. Each set is identical to the other. Each set is parallel to one of the edges of a pentagon. So it's tied in with the symmetry of the pentagon, which means you're looking at a pattern which has 5-fold symmetry. Not one that just has motifs with 5-fold symmetry. One in which the global pattern has the forbidden 5-fold symmetry. So that's striking. Now, you look at the lines more closely and you see if I look at any single one of them, they don't come in arbitrary spaces. There are actually 2 spaces that occur, either a long spacing or a short spacing. And if you calculate or measure what those spacings are, you find their ratio is a particular famous number, namely the golden ratio. 1 plus the square root of 5 divided by 2. 1.618, ... Okay, a particular rational number. That is telling you that the structure that you have there can't be periodic. In a periodic pattern, you can have sequences of lines of different spacings, but they would have to be in a rational ratio, a harmonic ratio, just like a harmonic sound. If you look more closely, yet again, you find the sequence of longs and shorts is quite subtle. It goes like long, short, long, short, long, long, short, long. Every time you think you have the sequence down, you don't. You'll find there's some switcheroo that occurs. And then you study it more closely, you find if I calculate the ratio of the number of longs to the ratio of the number of shorts as I go along, they follow a ratio of Fibonacci numbers. The Fibonacci numbers, in the infinite limit, that ratio goes to the golden ratio. So the number of longs to shorts also involves the golden ratio, which is, by the way, a rational number is very much tied up with the symmetry of a pentagon. If you calculate the ratio of the sides of a pentagon to the circle that circumscribes it, you'll find that involves the golden ratio too. And now you know something, because a Fibonacci pattern, a Fibonacci sequence is one that can be written explicitly as a sum of 2 periodic functions, where the ratio of the periods is irrational. Voila! Now you know what's going on. You've got something quasi-periodic. That's the definition of something quasi-periodic. So that's how we first realized that Penrose pattern actually has this secret quasi-periodic order. And once you know that, well, there's a lot known about quasi-periodic functions that you can now draw upon. So one of the things you can know about any quasi-periodic function is that it can be viewed as a projection or cut through a higher dimensional periodic function. In the case of the Penrose tiles, you can obtain them by beginning with a 5-dimensional hypercubic lattice, choosing a plane, an appropriate 2-dimensional plane which can project a certain subset of the points, and get the Penrose pattern that way. That means if you're interested, say, in the diffraction pattern for the Penrose pattern, you can obtain it by first taking the diffraction pattern of the 5-dimensional hypercubic lattice and perform an appropriate convolution to get the diffraction pattern of the Penrose pattern and see what that looks like. Or you can actually then do the experiment, if you want to do it that way, and do it the same way we studied diffraction in our early days of physics, where we shine it through a set of slits. So we shine it through a periodic pattern of points of slits, or a graphite paper, square lattice. You can form its diffraction pattern. You see that it's really made of the sharp-like points and has the symmetry of the crystal. We can now repeat that experiment now for the Penrose pattern, essentially reducing it on a slide like this. So high resolution, reasonably high resolution version of it, and reduce it on the slide and use it as the source of a diffraction pattern that I can use the laser pointer on for this, which is where I need to turn off the lens. I'm just going to walk next. So, oh, sorry, go to the next slide. I should have done that.
Okay.
Oh, 1 second. 1 second.
Huh.
My mistake. 1 second. Should put that down. So this is not the perfect experimental apparatus, so I'm only do so well, but we'll see how to do. Okay, you can begin to see. You can see that the pattern consists of sharp spots, and if you look more closely, you'll find there's spots within spots, between spots. It's imperfect because my pattern is finite, and my laser beam uses a lot of other speckle in addition to it. But you can begin to get the impression of what we're talking about from this experiment. And you can do it in a laboratory and find a way. Thanks, Eugene. And then, of course, once you have the secret of the quasi-crystal, you can learn that you're not stuck in a five-fold symmetry. Why don't you project from a seven-dimensional hypercubic lattice and make something with seven-fold symmetry, or 11-fold symmetry, or 17-fold symmetry, or choose whichever symmetry you want. And by the way, for every symmetry, there's a multiple infinity of distinct patterns you can make. So, how should I say? Almost all the patterns that you can make have never been seen by a human before because no human has generated them yet because of this multiple infinity of possibilities. And you can also do this in 3 dimensions with icosahedral symmetry. So in icosahedral symmetry, because it involves these 6 5-fold symmetry axes, the relevant higher dimensional structure is a 6-dimensional hypercubic lattice, which you then project into 3 dimensions rather than 2 dimensions. And then if you project a 5-dimensional hypercube into 3 dimensions, you get this shape, which I'll pass around. And it's known as a rhombic triacontohedron. And for those of you that know your Latin, you know that, first of all, it's made of rhombuses on the surface. Triacontohedron means there's 30 of them. So we'll pass those on. And you'll also notice that there's actually, in this case, you can't get by with just 2 units. We have 4 different units, which are represented here by the 4 different colors. You can kind of see that they're differently shaped. I'll pass this around as well. Now, what you'll notice about these is they have kind of Lego-like jointies on them when you fit them together. But when you fit them together, they're not all, you can already see it in that image, they're not all the same. So think about those lines I drew on the Penrose tile. There is some sequence of lines there, I didn't explain where that came from, but that had very special properties. That if you forced tiles to only come together where the lines join across an interface, that forced the Penrose pattern. This is the analog in 3 dimensions. Much more complicated construction, not directly derived from Penrose, but worked out now to the same degree. And if you look at the slits in the pattern, and you think of them as pieces of planes cutting through the surface, then if I gave you huge bagfuls of these tiles, you would find that the only way you can fit them together in this room is to form a quasi-crystal pattern with icosahedral symmetry. And those slits would form planes that cut evenly through that pattern. I should say evenly. They would cut in a Fibonacci sequence along that pattern along 6 different directions. So I'll pass this along as well, and you're welcome to put them apart and put them back together again, if you wish, before you pass them to your neighbor. And then just to give you a little bit more visual impression, what I've shown here is a layer, a single layer of the pattern. And you could lay on top of that the next layer, and the next layer, and so forth. And what I brought is those next 2 layers. I'm not going to pass around the top layer because it tends to be rather delicate and would break by the time it got to the second row. But I'm willing to pass this one. Please do not take this apart unless you want to spend the time it takes to put it back together. It takes me about 45 minutes to do that, so maybe you don't want to do that. Anyway, what this proves is that what this proved to us when we had done this theoretically, when we worked this out theoretically, was that you could actually imagine the materials mimicking the joining rules that you see in this, in these puzzle pieces, that are 3-dimensional puzzle pieces you see. And in that case, the state of lowest energy, the preferred state, would be this quasi-crystal pattern. And up to this point, there was this very strong belief, and many people even still believe it today, that the ground state, the lowest energy state of any arrangement of atoms must be crystalline. This shows that that ain't necessarily so. So, in fact, we had computed the diffraction pattern that you would expect if you were to look down the axis of a quasi-crystal, of a theoretical quasi-crystal, back in 1984. We're here, the idea of the pattern is that actually they're perfect point pattern, but we made the points have a finite size depending upon the intensity of the spots. And it was at that time that a friend visited me, a colleague visited me, and said, oh, there's this interesting paper I just ran into. It's preprint by Scheffner et al., which he didn't know we had done. He didn't know anything we were working on. He thought I'd just be interested in it because, well, he was interested in patterns generally. And when I saw this pattern in their paper, I was speechless. I just literally walked over to my desk and got that pattern. And that was the first time it was recognized that what had happened over here was that they had made something, they had shown that quasi-crystals might exist for real materials. We're just a hypothetical pattern, but was something potentially real. So he didn't understand why I was jumping up and down and very excited, but he came to understand. That's the simple version of the story. The actual story doesn't quite go as simply as that, because actually it's quite controversial for the first few years about whether the quasi-crystal picture was correct, or whether you couldn't explain Sheckman's material by some other means. So eventually Sheckman did win the Nobel Prize for it in chemistry, but it wasn't so clear what the story was for the first few years. Leading scientists, including Linus Pauling, one of the most famous chemists in history, were criticized the idea. He used to say, there's no such things as quasi-crystals, only quasi-scientists. And he wasn't completely wrong, to be honest, because Sheckman's material, well, that picture looks really good. If you actually were to measure that pattern more precisely, as you can with X-rays, you'd find that the points were not exactly perfectly point-like, the way they ought to be for a perfect crystal or a perfect quasi-crystal. And they weren't in quite the perfect positions that they ought to be in either. And this left room for alternative ideas. And so for the first few years, there were questions of, is what we're looking at a quasi-crystal that didn't quite reach perfection? Because it's hard to make perfect crystals as well. Or is it something else altogether? And the subject got settled a few years later, with not any further work on checkmark material, but work on a different material, this mixture of aluminum, copper, and iron, which now, instead of producing this disordered looking thing we saw before, is producing something beautifully faceted with pentagonal facets arranged in a dodecahedral solid pattern, which has the same symmetry as my icosahedron. And for this pattern, we took the diffraction pattern to the degree to which you could measure within your instrument. It was really point-wise. And the points were really on all the right spots that were supposed to be. And at that point, the community conceded, yeah, quasi-crystals exist. And that was an important moment, because it meant really now we had to open up our ideas about what forms matter can take. But there was still disagreement about why they form. And some of that disagreement, if you agree, is the same, remains to this day. Because in the laboratory, when you make a quasi-crystal, you make it under highly controlled conditions. And there was this idea that quasi-crystals are actually very delicate forms of matter that would not survive very long before they were crystallized. And it's important to know whether that's true or not, because if that were the case, then any application you should ever try to make of quasi-crystals to take advantage of the unique symmetries would be short-lived. Would be a short-lived success, because your material would transform to crystal and you lose the special properties you were looking for. But it was important to understand this from a practical point of view, and also important to understand from a fundamental theoretical point of view. Because that puzzle pieces I passed around show that, at least in principle, mathematically, there's no barrier to having a stable quasi-crystal, or one that's arbitrarily long-lived. So this was the state of affairs in 1987. So it was in thinking about that question that I was led to ask the question, is it possible that the first quasi-crystals made were not made in a laboratory in the 1980s, but it made earlier, maybe hundreds of years ago, maybe thousands of years ago, maybe millions of years ago, made by nature. Maybe nature is beating us to the point. Maybe we shouldn't be looking for laboratory tests. Maybe we can learn something from nature and see if there's such a thing as a natural quasi-crystal. Because after all, we discovered crystals first in nature before we discovered them in a laboratory. And so began a project to look for so at first, back in the 1980s, when I first was hit by this idea, I began to simply go to museums which had large collections of minerals, and just see if by chance there was some material that had been mislabeled. I went to the Smithsonian Museum in Washington, the American History Museum in New York City, and others. Never had a chance. And I'd always try to look there and talk to curators there and see if they had any examples, but that idea didn't work. By the late 1990s, about 15 years later, I had changed strategies. I thought what we could do instead is look systematically for them. It turns out there are big catalogs, computer catalogs, collections of what we call powder diffraction patterns, which are, I won't explain what that is in detail, but it's a kind of diffraction pattern, which we could then develop a mathematical algorithm to sort through and look for which samples in that catalog were good candidates for quasi-crystals that we should follow by actually checking the material out. And in that catalog, it included refraction patterns of around 8,000 minerals. So I was looking for, restrict ourselves to 8,000 minerals, and then see which ones came closest to satisfying the mathematical criteria we were looking for. And then going out and trying to find them, test them, bring them back to Princeton, where I was at the time, and try to measure them there. And we had some really wonderful adventures doing that, but complete failure after failure after failure. So finally we wrote a paper, and we said, announced, okay, we have this way of doing this catalog of candidates to look for, and this was 2001. We said we welcome anyone that wants to join into this venture to help us look for natural quasi-crystals. So that might sound good, but in fact, no one answered the call. until May 2007, when someone I had never heard of before, some fellow who comes from, here, Luca, answered the call. He had read the paper. He said, well, I've worked on some related material, unusual materials, and I'd be happy to join your venture. And fortunately, I took him up on the offer because he seemed, there was something about the email that made it sound unusually sincere and dedicated. And that was really, really incredible stroke of luck, because it turned out for two reasons. Most importantly, because Luca turns out to be one of the most amazing people I've ever met in terms of not just his talent, but as a scientist, but his enthusiasm and joy of doing science and absolute fanaticism in pursuing the project. As fanatical as I was. So we were really, we very quickly formed a bond that was, even though we had not yet met in person, all our communication at the beginning was just through Google Chat. We quickly formed a bond of pursuing this unlikely, impossible goal together. And then, but the first year didn't particularly go brilliantly. We looked through a bunch of materials on our list, and it was, again, failure, which was consistent with what had been found before. Basically, the catalog we were drawing from was not precise enough to be useful for its purpose. And then he pointed out he had some things in the basement of his museum and a sample, which was not in our computer catalog. But it was a mineral which had composition of aluminum, copper, and iron that he thought, reminded him of quasicrystals and might be a good candidate. I know he's giving a talk, and he might have said more about what inspired him to make that choice, but it was an inspired choice. Here's the material itself. It was what we call a micromount, so it's a very small sample. It's entitled Caffè-Scienza. That was its official mineral name, so it was accepted as an official mineral. It was a mixture of aluminum and copper. It says it comes from Katirka, wherever that is, in the Koryaks of Russia. You can see it's small. It's actually, if you're in the back, you might be thinking that whole lump is the sample, but that's not true. Most of that lump is just a piece of plasticine, which is holding the sample at its tip. If you take a picture of the sample at its tip, now it looks like something significant, but remember we're talking about something not so big. Okay, and it's pretty complicated. It's not a mineral, it's not a pure mineral, it's a rock. It contains lots of minerals, some familiar to us, very familiar to geologists like the dioxide and olivines, but also that black stuff is some kind of, turns out to be various mixtures of metals. And then what Luca did is what we normally do when you're trying to look for something new in a sample, he sliced it and diced it and might try to make a section of it so he could look through the middle of it, not the outside of it. And then he performed an experiment using an electron microscope that began to sample different points in the sample, and with the electron microscope you could measure the chemistry around a different point. And you find the different colors correspond to completely different chemistries. So for example, the yellow turned out to be aluminum copper 2, which is in fact the chemical formula for Caffè-Scienza, the mineral in the International Mineralogical Catalog. So the sample of Caffè-Scienza had Caffè-Scienza in it, which you might think is obvious, but you'll see it's not so obvious. That was lucky. It also had another material in it, which was copper aluminum, so 1-to-1 ratio, which is another mineral in the International Mineralogical Catalog, and it's called cupellite. Then it had green stuff and blue stuff, which had compositions that should correspond to anything in the catalog. So they were the obvious targets to check. In addition, and the green ones turned out not to be interesting, but the blue ones, when Luca tested those with the instruments here in Florence, seemed to be strongly hinting that they might be quasi-crystals. But you couldn't do yet the definitive test with the instrumentation here. We had that instrumentation at Princeton, so the sample was sent to Princeton. Before he did that though, he actually used a fine needle and somehow, by some magic, managed to poke out the blue material from the rest. So by the time I saw it, I never saw the rock, I never saw the slice. I saw almost invisible powder. Now, I have to say, my dream was someday to find a quasi-crystal this size. And instead, I found something I can't even see. So, nevertheless, we managed to take that powder off the needle which he had sent it to us, glued it to, and the day after New Year's Day, 2009, got up in the middle of the night because that was the only time we could get access to the transmission electron microscope there, took the material off the end of the needle, put one of the thinnest grains on there, we need a thin grain the electrons can go through, and took a look at the thinnest end of it, which was up in the upper right in that circle, and immediately appeared this magnificent diffraction pattern. Magnificent. This is an overexposed picture of that pattern. The pattern in the microscope looks exactly like it. It looks like a textbook quasi-crystal pattern. Perfect. More perfect than anything I had seen even from synthetic materials. So there was no question that we had found what we were looking for at that point. But there was also a question that arose. What was its composition? Well, that took a few days before we could measure its composition. When we measured it, we found it was 63% aluminum, 24% copper, and 13% iron. And that was, wow. Wow, can you imagine that composition? Why would we care? Well, because that was a composition we knew already. It was a sample of that sitting on my desk in Princeton. It was a synthetic sample made by the Japanese group back in the 1980s. What we had found was something which had the composition that was already known, and within the same measurement range. There was no question that what we found was truly quasi-crystal, because we already knew that was the case for the synthetic one. However, the synthetic one was made under highly controlled conditions, in vacuum, isolated just the right composition of aluminum, copper, and iron. Made sure they couldn't interact with oxygen or other gases or any materials in the area, and then cooled very carefully and slowly under ideal conditions. And that got a very perfect pattern. Here we got a very perfect pattern by taking material out of the slice, which is a complete mess, as you can see, of different phases, including the phases which contain oxygen, which aluminum interacts with very strongly. And this would be the last way you would think to produce a quasi-crystal, based on what was known. So, question. Well, I should say, at this point, we could have stopped the project and simply sat at the rock and been done with it. But no, we were too curious. The question of how did this thing form? What did nature know that we didn't? Because nature figured out how to do this, but we wouldn't know how to make it in this environment. Well, what does this tell us about nature? And what does this tell us about quasi-crystals? So neither Ruben nor I could answer that question. So we decided to consult someone we thought might be able to. And his name, he was a professor at Princeton. He was a professor at Princeton, he's now emeritus, who is in the Department of Geosciences there. His name is Lincoln Hollister. Lincoln is a famous petrologist, one who studies the origin, who by studying rocks figures out the origin of how they form. So he's the right kind of person to find to ask that question. He also was one of the first persons to analyze rocks recovered from the moon, and made many other important contributions to geoscience. So he was the right person to consult. What I didn't know, because I had never met him before, is called, I just wrote an email and said, "Would you meet me?" He said, "Yeah, sure." What I didn't know was that he was famous as a pretty tough character. He didn't brook nonsense. If you brought it, and here I am, a theoretical physicist who doesn't know anything about minerals, coming to ask me a mineralogical question. So I I didn't realize that I could be entering some trouble. His office is on the 3rd floor, and there was the possibility that if he got upset, I might end up in front of the window. And so, I really didn't know what I was getting into. I knocked on the door, I came to the door, and I told him the story that I told you up till now. And he was quiet after that for a few moments, and he began to give me a look that I learned later was a sign of a red flag. Something bad was going to happen. And then he quietly said, well, I'm sorry to tell you that what you have there is impossible. And I said, well, no, it's not impossible, because we know you can make quasi-crystals in a laboratory like this. And he interrupted me and said, I don't know anything about quasi-crystals, but I'm telling you what you have there is impossible. Because you're telling me what you have there is a material with metallic aluminum, metallic copper, metallic iron, all mixed together as a metal alloy. And there's plenty of aluminum in the earth. It's one of the most abundant elements of the earth. And if you have a sapphire or a ruby, you're building an aluminum oxide compound. Okay, there's plenty of aluminum, but aluminum is voracious and a voracious appetite for oxygen. And so all the aluminum you find in the earth is attached to oxygen. And so there's no way you can make something like that naturally. And I had encountered the word impossible by this point in my life at that point many times. And it was like a mantra that I recite in my head when I hear that word, that came out of my mouth, which was, do you mean the first kind of impossible or the second kind of impossible? Do you mean the first kind, like 1 + 1 is 3? Or do you mean something like something you have never seen before, but and so we think it's unlikely, and maybe you decide it's not possible, we can't actually prove it. That's the point when he might have thrown me out of the window. But fortunately, he didn't. Instead, he thought for a bit and said, well, if I'm forced to come up with an explanation, here's an idea. In order to separate the aluminum from the oxygen, you need extraordinary pressures. The kind of pressures you need deep under the earth, not just a little deep under the earth, but near the core mantle boundary, so quite far under the earth. Then you can separate aluminum from oxygen. But then, of course, you have to get your material up to the surface of the earth. But, one of my colleagues here is one of the regional authors of plate tectonic theory, and he has always had this idea that there might have been super plumes that brought material all the way as deep as the core of the earth up to the surface. When I heard that, I'm thinking, it's the second kind of impossible. There is a possibility. It's not absolutely impossible. Then I threw out an idea that I had been thinking about. I said, well, how about meteorites? Meteors, I should say. How about meteors? After all, in space there's no oxygen, maybe that's a place where that can happen. Now, I didn't know it, but that was an absolutely idiotic statement. It showed my complete ignorance, because there's plenty of oxygen in space, there's plenty of oxygen in meteorites. My good fortune was, he didn't know that. So he didn't throw me out of his office. Instead, he said, I know nothing about meteorites, but I know someone who does. He's the director at the Smithsonian Museum of the meteorite collection. He's an expert on meteorites. His name is John McPherson. And so that's how, a week later, we ended up on the train to Washington, D.C. When we got to Washington, D.C., we went to Constitution Avenue, where the museum was on. That's on that street, and walked up to the door. Apparently, I didn't know it, but Lincoln had already broadcast to Glenn that I was about to arrive at the door. And Glenn was waiting at these giant doors from that museum for us. And because he couldn't wait to tell us what he wanted to tell us. I didn't know he also, Lincoln had called him in advance. He told him the story that I just told you up to this point. And he wanted to tell us right off the bat, before he even entered, before he even got us through security, before he brought us to his office and all that. He wanted us to right off the bat that what we had there was impossible. And for the next 3 hours, we got a long lecture on how ridiculously impossible it was. He had seen every form of meteorite ever seen, and he knew that what we had there could not be possible. No mathematical loop has ever been seen in the meteorite ever before, he reported to us. And he began to give us various reasons. I won't go into all of them, why other aspects of our sample were inconsistent with being of meteoritic origin or being of natural origin. Instead, he concluded by uttering a four-letter word that said, "You just have a piece of slag." I don't know what you were thinking. But piece of slag, something that was a remnant of some sort of human activity. And then he sent us on our way, and I'm sure, Lincoln bought everything Glenn had to say, and I'm sure they thought they would never hear from either of us again. But when I contacted Luca, there was a sad email I had to write to Luca about the report of that story. We pretty soon, it was almost immediately decided we weren't going to give up yet. We still had to understand where this material came from and how it formed. Even if it was a piece of slag, how do you make a quasi-crystal diamond? So it seemed to be like a no-lose position, just to continue the project. And furthermore, I guess this was my decision. We weren't going to let these two guys go. Because they were very useful. They were extreme critics of whether this was something natural or not. And sometimes when you are pursuing an idea, you're a very strong proponent of that idea. You have to watch out that you might fool yourself into believing something that's not true just because you're psychologically, particularly a booster of the idea. Sometimes you can get some separation, sometimes you can't. In this case, my fear was that we couldn't. And so then it's useful to have strong critics on your team and have them be your critics, have them be what I call the red team, while you be the blue team. And now it becomes a competition between the red team and the blue team. Blue team tries to give more information and tries to convince the red team. The red team pushes back and says, why it's not good. And you go back and forth on this. And this seems to me to often be the best way to reach a truth in a situation like that. I try to do that in a lot of the investigations that I work on. It works very effectively. So Luke and I were the blue team, and our job was to answer two questions. Number one, did this sample really come from where it said in the box from the Koreatic Mountains, which is a remote place in the world, nowhere near any aluminum smelting or any other human activity? And number two, can we prove with a little bit of powder that we have left in the sample that it isn't slag, that it's really something natural? And that's what we were, that began the process of the next year and a half or 2 years, struggling, trying to squeeze every bit of information out of that we could about these samples. So I'm going to focus on the misstep and the first story, because that's the part, the second question is a more typical scientific story of lab studies. But the more bizarre story was trying to do essentially the detective work, an international detective story, to determine where that sample really came from. Did it come from where the box said or not? By the way, you might assume the box is correct in the label, but you shouldn't, because we found plenty of examples where that has turned out not to be the case, as I'll mention in a moment. So what would you do first? Well, first thing was to ask Luca to go check the records of the museum to figure out where the sample came from. We discovered that there was only a piece of paper that explained the sample was one of 3,000 micromounts that were sold all at once by a collector from Amsterdam. And it gave us the name of the collector, but it didn't tell us how to reach him. But it was the day of the internet already, and you could go searching through the streets of Amsterdam and looking for people, and we tried to do that, but we didn't find him. So that was the end of that trail. Next, we began to send almost simultaneously, we began to send all point bulletins out to museums and collectors around the world to see if any of them had samples of the same type of material that we could investigate independently. And I think it was like 5 places responded, 4 of whom were in the West, one of which is in Russia. The 4 in the West sent us their samples so we could study them. And pretty soon, that's to say, literally, almost within a day, we discovered each individually, in each case, each of those samples turned out to be a fake. I mean, by fake, I mean, it didn't have the right chemical composition. It was labeled Caffè-Scienza, but it didn't have the right chemical composition. Here's where we learn something sad about the story of mineralogy as it meant in the mineralogy collection, which is there's a lot of fake. If a new mineral is announced, and these were fairly recently discovered, compared to most minerals, you go to a rock show someplace, and you'll find samples. In fact, you might even, for all I know, you might go to a mineral show today and still find people who claim samples to have Caffè-Scienza. Now, when you buy an expensive piece of art, the art is very expensive. Having it checked for its provenance is relatively inexpensive compared to the price of the art. So you willingly pay to have it tested before you buy it. With minerals, the economic situation is reversed. The mineral is cheap compared to the cost of testing, because that requires expensive equipment. So what will collectors do? They'll buy that material, they'll put it in the collection. They may even someday sell it along with the rest of their collection to a museum, and then it finds its way into a museum which also does not test. And this apparently is what was happening to these 4 samples in the West. So, watch out. Don't buy Caffè-Scienza unless you test it. The sample from Russia, though, is one that had to be correct, because that was what we call a holotype sample. The first example that was, the example that was passed before the International Mineralogical Association to decide whether it should be accepted as a new mineral or not. And it appeared in the paper, which the lead author was a fellow by the name of Leonid Razin, and not only did his sample have Caffè-Scienza, but his sample he reported also had the Kupolite, which was good news for us because we had both those materials in our sample. And so all we had to do was go to the contact the St. Petersburg Mining Institute, get them to give us the sample, and we could test it. But that didn't work out because that institute was run by a dictator who wouldn't permit anyone to touch the holotype sample. The holotype sample, because of its official nature, is the official sample that you have to put into a museum and have it officially accepted. He was insisted that it not be touched, even though what we would have done, we would have done little damage to it. Full effect. So what could we do next? Well, the next thing is, could we find this guy named Razin? So again, today the internet is beginning to vast around throughout Russia. Where's this guy? We discovered that he was quite a well-known character, not a particularly good character. He had strong to Soviet Russia. He had strong political connections in the party through his family, including KGB connections. He was known for punishing his competitors by getting them into various kinds of legal or official trouble. He was not a particularly respectable scientist, one that people trusted. And so we heard a lot of bad things about him. And finally we heard he was no longer in Russia. He had moved to Israel. So, okay, we're trying to track him down now in Israel. I'm looking through, I'm on the internet and I'm looking through telephone books in Israel. I find someone with that last name, but in fact, that name didn't blossom in a telephone book of someplace outside of Tel Aviv. And I call, but they don't speak English. So I got someone who's a Hebrew speaker to call. They didn't speak Hebrew either. So the third caller was Russian. They spoke Russian. And I finally got him on the phone and I asked him, are you the lead Razin of this article? He said, yes, I am. I'm sorry. First he said, I am Professor Razin, because he wanted to be a very efficient discussion. So he said that, and then I asked him, are you the person who dug this material out of the ground? He said, yes, I am. I said, do you have your geological notebook? Because I have been warned by geologists that if you're a geologist, you sleep with your geological notebook. It's something you always know where it is. And unfortunately, what he said was, I don't know. It might be in Moscow. That's a red flag. I really know that's a red flag. And they said, well, is it possible you have more samples back here? He said, maybe back in Moscow. And I said, in the meantime, I've already worked on working on the side of the internet pricing airplane flights to Israel and Moscow. Saying, would you be willing, if I paid for you to go there, to go look for your notebook and your samples? And then he hesitated. And it took different back and forth and fencing. No, I don't want to do it. Hinting more and more that you have to give me a little bit more extra money if you want to do that. And then I tried to talk to other people who knew him and see if they would talk to him. And it turned out he wanted to get a substantial amount of reward for this. Even though I was explaining to him, this material has no intrinsic value, it only has scientific value. And by the way, I'm not a worthy scientist. So, we don't have money that we can really offer you beyond, nice travel too. And then he held out. At that point, I had to make a decision whether to stick with this guy or to forget it. And I was very concerned about what I've already told you about him. The fact that he didn't have his geological notebook. I was worried that he would come back with a notebook, and I couldn't tell him I was written. It could have been written yesterday before. And he might say, I don't have any more materials, and then, okay, where am I? I'm lost. So it was a difficult decision, but at the end of the day, I decided to drop this case. So now every direction we had explored, it turned out to be a dead end. Then that should have been the end of the story. But it wasn't, because one of those miracles that I already told you, when the various barriers got in the way, there'd be some miracle. In this case, the miracle happened here in Florence. I think it was in Florence. Luca was having dinner with his sister and a friend, and it was time the story I told you up to this point, and the friend interrupted it at the end of the story and said, near the end of the story, said, what's the name of this guy in Amsterdam? He told me the name of the story. Because I live in Amsterdam. Maybe I heard of this person. He told him the name, and he said, that's too bad. His last name is such a common name, that you're going to find many such people in Amsterdam. It's like Smith in the United States. I don't know what the equivalent would be here in Italy, but it's too common a name. He said, there is a woman down the street. I help her with the groceries occasionally. She has that last name. When I get back to Amsterdam tomorrow, chat, see if she heard of him. And within the 24 hours, comes back an email to Luca that announces, guess what? She's a widow. So, okay. Good news and bad news. We found he's no longer alive. But that doesn't stop us. Luca's in Amsterdam the next day with a friend, with his sister's friend, and they're trying to get the widow to to visit the widow to see if she will give them information. The widow will not see Luca. She's too afraid, but she will see the friend. The friend decides to try to ask her if she knows anything about her husband's collection. No, she said, I know nothing about it. That was his business, and he gave the collection away. He's not satisfied with that answer. He asked the question a different way. No, nothing. I have nothing to do with it. Another way. No, I know nothing. Really know nothing. I'm saying nothing. Finally, she's getting tired and says, oh, except she says, my husband used to keep a secret diary. The secret diary, sure enough, it says, has the husband going to Romania, and suddenly it says something about exchanging something, and comes back with this mineral. So obviously, what he was dealing with was a mineral smuggler, because taking minerals out of Russia at that time was a legal offense. And so he was a smuggler. And furthermore, gave his name. The name of the Romanian smuggler was Tim. Tim, the Romanian smuggler. When I heard that news, I thought, great. It shouldn't be hard to find Tim, the Romanian smuggler. How many smugglers in Romania are named Tim? But after weeks of searching on the internet for Tim, the Romanian smuggler, kind of contacts here, and even to this day, I've never found Tim, the Romanian smuggler. So again, dead end. You can see how the story goes. And I'm going to give you examples of constant dead ends. Finally, decided to take another shot at the widow. This time Luca is admitted, and he participated in the conversation. But it goes the same way. She knows nothing. She's given everything that she has. Nothing to do with it. Nothing to say, nothing to add, nothing. Except her husband used to keep a secret diary. Here's a piece of the secret diary, or at least the notes she would take it from the secret diary. And then there's an entry to Tim, which I got Tim. And then it's telling you where he got his material from. He got it from this guy, our friend Rossi. So now we know that our material is not only similar to this material that Rossi reported, it's actually a piece of material that Rossi reported. So all we have to do is figure out where Rossi really got his material from. By this point, we were pretty sure that Rossi was much too fancy a guy to go out in the wild someplace and do his own digging. He would send someone for it, because he was upper class in society. And we only had to figure out who it was. If you look back in the original paper, it begins with a story which doesn't connect directly with the theme of the paper. The paper is a story of Katirkite and Kupalite. The first author there is our friend Rosin. There's a second guy, Matuszewski, which was the lab, which is also mentioned in that reference to Tim. And there's a third guy, Vyacheslav, who played a minor role. But in the middle of the story, in the middle of that first paragraph, it mentions the name B.B. Kryachko. And it mentions a stream called Melissa Utovia. So I can't tell you how many hours I spent in maps looking in the library for a stream called Melissa Utovia near the Katirka Mountains, which it also describes. When I showed this paragraph to Russians, they explained, look, this guy was the head of the Institute of Platinum at the time. His job was to look for extremely valuable material, platinum. And that's what this project was really about. This was an accidental byproduct of such a search. Now, what he doesn't want to let people know is where he's searching for platinum, because he doesn't want to be scooped. So he's not going to tell you on the story. He's going to write some fictional paragraph over here, which actually has nothing to do with the story, to throw you off your scent, throw you off the scent. So this guy from the garage show doesn't exist. Then later, because I kept asking this question every time I had a chance to do, another set of questions says, oh yeah, that's a real person, but unfortunately he died. Another member of the Russian Academy of Science later told me, no, that person is very likely a native Chukchi, native of the region, who would just disappear into the wilderness after digging in the list of the Utopia stream and producing these samples. You'll never find that person. So it was one of those things on our list, one of those dead ends. But suddenly it became a life. Because Lucas found a paper which had this guy listed as an author. And for that, you could go to the co-authors and see if you could track the guy down. That's how I ended up talking to what turned out to, I didn't know at the time, to have been his PhD thesis advisor. And when I called him, again with a Russian translator, I discovered that I asked him, does he know this guy? Yes, he knows this guy. That was his PhD student. Okay, finally some real verification. He exists. He's not a figment of the imagination. He's not a Chukchi native. And he said, I even remember that he had gone through this adventure, this unfortunate adventure, this horrible guy, Raza, who was a very weak character, not a very, I'd say rather evil character, and he told his advisor about this experience. His advisor, so he knew everything about it. And finally asked the question I was most afraid to ask, namely, is this guy still alive? And he said, yes, he is alive. In fact, he's coming to visit me next week. You want to talk to me? So suddenly it went from a fictional character to someone I could actually communicate with. Not in English, but we could communicate through Google Translate, once again through chat. And he immediately, dear Professor Steinhardt, began to spill out a whole story of how he was sent to Russia in 1979 to look for obscure stream in the Koyak Mountains, a remote place, to look for platinum. He had collected samples and worked like crazy to find samples. He found sharing samples, but he knew they weren't platinum. They didn't have the right density. They didn't find any platinum. And the one thing he was afraid of was to come back to rosin and come up empty-handed. So instead, he brought these shiny materials with him, gave them to rosin, and that's the last he heard of them. He didn't know that rosin brought them back to St. Petersburg, had them tested, discovered a new mineral, published a new mineral, without, by the way, including him as a co-author. And in fact, smuggled some of it out, and some of it ended up in Florida. He knew nothing about that. But by this point, the news that Luca and I had discovered, and collaborators had discovered a potential natural quasar crystal was out. He had heard that story. And so he was immediately excited to discover that he was part of that story. He didn't know that from what information that had come out. And was very open about it, not just giving us details, but even giving us details as to where on the map we had discovered that material. So suddenly we had a lot more information. And he also offered if ever we wanted to go back, which sounded like a crazy idea at the time, he would help us do so. So when Lincoln heard that, he began to turn from red to purple, somewhere between blue and red. Glenn was still pretty stubborn. In the meantime, we were doing these tests on the real material and trying to check whether or not the material was little bits of powder we had from the wheel or not, or whether we're looking at slag. And every time we had a test for slag or showed it to people who were experts on slag, none of them thought it was slag. So it began to build our confidence. But the key test was to do a test of the clincher test would be to test the ratio of rare oxygen isotopes in the sample to see if they would point us, if they would indicate where the material came from, whether it was terrestrial, slag, or from space. And that experiment again requires special equipment that is only available in a few places, including at Caltech. And so we got the Caltech group to work with us on this project. And when they came back after a few months, took a few months to get the result, and they came back, it was unequivocal what the result was. What we had there was a piece of a meteor. The meteor idea, we had 12 different theories. By this point, it's collapsed to just one idea, which this had to be a meteor, which had undergone some high velocity impact sometime in its history. This is just an artist's visualization. And not just it was a meteorite, not was it just a meteorite, but it was from an asteroid, from a meteor that dated back to the beginning of the solar system. It was a special kind of meteor. It's called a CV3 carbonaceous chondrite, which is some of the oldest materials that were formed in the solar system. Studied by probably the most studied type of meteorite. In fact, the world expert on CV3 carbonaceous chondrite was none other than Glenn Pearson at the Smithsonian, who had told us unequivocally that what we had couldn't possibly be natural, couldn't possibly be a meteorite. When we saw the data from this experiment, he didn't go from blue to purple, he didn't go from red to purple, he went from red to blue. So immediately said, what you have here obviously is exactly the kind of meteorite that I've studied. Now you have to give me a lot more sample, but there are many other questions I want to ask about it. And he said, Glenn, guess what? We just used up all the material trying to do all these tests to convince you that it was natural. We had no more material. When we even get more material, Glenn, is, you'd have to go back to Jakarta. In Jakarta, it's impossible to go back. And even if you went back, the chances are you'll find something. You'd have to get permission from the Federalia Služia Bezopernasti, the FSB, the modern KGB, which you can't get. You're going to have to get Valery, who's now in his late 60s, to come with you. You're not going to get that. He's the only person who would know where to look. You're going to have to get members of the Russian Academy of Science to join with you. Who are they going to be? It's going to take that risk to try to do that. You're going to have money, because it is going to cost something to get a team out there. You're not going to get money from the U.S. government. You're not going to get money from Princeton University. You're not going to get money from National Geographic. I already tried all those places. You're going to have to find some way to get money. We need a good friend of physics. You're going to have to get Luca to go with you. I'm not sure what Luca's thoughts were at the time. I don't think he was necessarily enthusiastic about going at the beginning. Thank goodness he changed his mind. You're going to have to get people who have different kinds of expertise. Someone like Chris Andronicus, who was a structural geologist who wanted to learn the structural geology of the region where it was found. But he also had to do work with grizzly bear, National Grizzly Bear Park in Canada. So he was familiar with this kind of geography, in particular on bears. And he did give us bear lessons. I remember that bear lesson very well. He talked about, and if you see, that these are some of the most vicious bears in the world, on the level of grizzly bears. And he talked about becoming big, shouting loud, making yourself, trying, if they're distant enough in distance away, doing all kinds of things you can do. At the end of the instructions, he pointed out, by the way, it really makes a difference, not makes no difference about what you do. You're dead. So that was encouraging. You're going to have to get someone who's a meteorite expert, and you have to get Glenn to go. Glenn had been in this, but he's not a field geologist. So what are the chances of getting him to go after all this? You're going to have to get someone who speaks English and Russian, because half the team going speaks only Russian, the other half of the team speaks only English. And somehow we have to go to talk to one another. So you have to get someone who can speak both, and that was Alex's idea. Alex's as well. You're going to have to get muscle power, and you know what that means? Students. So when we get students who are stronger than the rest of them, Michael Eddy was actually a championship runner at Princeton, and also a geologist, so he came along with us. And then this character written on, this is someone that actually literally known since he was a baby, because that's my son, Will, who at the time was a Caltech student in geoscience, about to move to Harvard. Geoscience, and he had outdoor experience. And this was a great, humorous opportunity for him to make a lot of fun of me because, I should explain. I'll hold on and explain that in just a moment. You needed people who were going to be able to take you across the countryside. You need drivers like Bowden and Victor. You have to be able to make a lot of arrangements in Chicago in order to do this. That means you have to be able to interact with the politicians, you have to be able to interact with the lawyers, you have to be able to interact with the police, you have to be able to interact with the businesses. It wouldn't have hurt if you were also a good cook. Olia had all those properties. And she was a wonderful addition. She was the wife of Victor. So we had that team. Then you have to worry. There are dangerous creatures out there, mainly giant bears. What are you going to use for protection? Bucks the cat was our protection. Bucks was very successful when we were not attacked by pigs. He was also a pleasure to have him. He was the bravest. He would walk bravely around while the rest of us are looking around. Every now in the morning, he'd walk around and see a giant bear footprints. The bears were around, but just didn't find us delectable. So at that time. And so there we were on July 2011. And ready to take off. And these two strange vehicles have five Americans, 7 Russians, 1 Italian in the middle, and also in the very front, in that basket over there, with 2 shining eyes above. It was a great team with a lot of geological experience, outdoor experience. There was one guy who knew absolutely nothing about outdoors. That was me. I'm a theoretical physicist. At this point in my life, I had not even camped outdoors overnight once. Not even and I'm supposed to, quote unquote, lead this team. So fortunately, they were great. They didn't need any leadership. And I also had a tent mate, my son, Will, who just delighted in the fact that he knew everything. And I was at the baby in this situation. I had to get camping lessons. ABCs. I was trying to check things Okay, so this is what it was like to ride these vehicles. Let's see. I can't put the sound on. Well, let's do it with soundless. So when you're riding across the tundra from the distance, it looks like flat land. It looks like it's very peaceful. In practice, when you're riding across the tundra, it is the most difficult. It is like an up and down roller coaster ride. You can't even walk across it very easily. In fact, the local natives there are famous for walking kind of in a strange way. It's because that's the way you have to walk if you don't want to sprain your ankles constantly. And this is what it was like on the ride. This would be a typical experience. I'm going to go for a moment. I think that's a good thing. There are two of these guys. They seem, sometimes they seem invincible. Like they were riding with Victor, right? He's the Victor. I'm looking at him saying, "Where's the trail? Why are we running off the trail?" It could be a funny look, right? Trail. For those of you who are worried about the trees, don't worry. But there were scary moments. This is one of them when we had to cross the table. We were in an area where permafrost night, you have no idea what the depth of the river is, and you have to cross it. And these vehicles were supposed to float, but no one had ever tested them. Nobody people quick. Yeah, actually did float. And by the way, let's go to the other end. We're going to get back to that crossing once again. So you can't anyway. So yeah, so that was challenging. Another challenge was the billions and billions and billions and billions and billions of mosquitoes that you had to fight. And as I said, there were bears. And our bear expert, Chris, had told us if you see 5 or 6 bears in the whole pack, you should know that that's just the beginning of a multitude of bears. We didn't see 6 bears, we saw 24 bears. So we were definitely in bear territory. And fortunately, it was really good salmon season that year. So I think they were interested more in the salmon than they were in us. And so we didn't really have direct trouble with it. When we got to the site, here's the site where in 1979, Valeria in the middle had dug those little samples up, one of which ended up in Florence. And I think I don't have to explain who the other 2 people are. And then the work starts, and the work included, digging, panning, a little makeshift laboratory for studying samples. Chris and Mike were doing the structural geology measurements, and we worked as hard as we could for the next 10 days. On the bottom right, you're seeing digging with a shovel. Those shovels, that was the first few minutes of work in the field. Shovels broke within those first few minutes, so the rest of the work had to be done by hand shovel. And essentially most of it done by wheel, about nearly 2 tons of material brought out and then panned into separates by using Russian panning technique. Here you see part of that process where you begin a lot of that material, and then you're panning out the water and the light material because you're looking for the densest material. In this particular case, there's a little glittering something there. You might see that. That turns out to be gold. We did discover gold. A lot of it. Here it is. And in fact, that's what the stream had been used for, as a gold placer site. Where you kind of hunting for gold, and often you find gold, you find platinum, and that's why Valeria had been sent out there back in 1979. Notice that he's wearing short sleeves. So for the first 9 days, you could go with short sleeves. By August 3rd, the fall had come to Chicago. It's close to the Arctic Circle, and so we're all wearing now these much warmer jackets. And the next day we took off, and then the next day when we looked the next morning after that, we looked back and winter had come to Chicago, the Korean Mountains. We had barely escaped just in time. We would have been stuck and needed to be rescued had we not gotten out exactly when we did. So we got the maximum time there. When we finally arrived back in Anadir, we got together in a room and reviewed all what material we had found. You could not tell from the field anything that you had found because you don't have the right instruments for it. But we did make bets as to what the probability was that we had found a quasi-crystal. I bet 0.01%, 1 part in 10,000. Others bet different amounts, some higher, some lower. The person who gave the highest percentage bet was Luca. He bet 1%. So 90%, the chances that we had failed was 99% so far as we were concerned. And you don't know. Next thing you have to do is manage to get the material out of Russia, not trivial, because remember, taking material out of Russia can be a questionable thing. So develop a complex scheme where I made sure different people had different, we were taking different routes back, had different subsets of samples. And so if some of them got stopped, maybe some of them would get through. In the end, they all got through. So, and then we had to bring them back together, and then we had to get them over to Luca, because Luca is the normal democracy. He makes all the miracles happen, including being willing to look through millions of grains to look for what we were looking for. Now, he had a favorite grain that he had pointed out when he first discovered it. He'd come to me and said, on the first day out, I think we've already found one. Glenn didn't believe it. Glenn was completely skeptical, right? And so we didn't know what to think. We couldn't test it in the field. But a few weeks later, in fact, presented that sample. And in that sample was this shiny bit of material which he removed, and then took an X-ray diffraction pattern of it, and it produced a beautiful tenfold X-ray diffraction pattern. And it had the composition that was just complete agreement with what we had found in the fluoride sample. Now, I can't tell you what an incredible moment that was. Because up to this point, what did we have? We had this fluoride sample, which still could have been a piece of slag. We could have, the trail that brought us to the widow, and brought us to tin, and brought us to rosin and all that. We could have made a mistake along the way. And maybe we were following the wrong trail. There were a lot of false trails, and we did follow the wrong way. We could have done the wrong trail. Here, by following that trail, we actually know exactly when that sample was found, where it was found. It was found in material which had not been disturbed for 15,000 years based on carbon-dated studies. So we know exactly where it's from, and it matches exactly the sample that we had at Oregon Florence. So that led to many exciting developments. That was like we actually figured out the story. We actually had something that's natural. That was enough to convince the International Mineralogical Association to accept icosahedrite, as we called it, as the first quasi-crystal, the first quasi-crystal sample to be accepted as a natural mineral. And and that could have been the end of the story, but it wasn't. Over the next years, with several groups, including Luca, looking for the samples, we found up to 9 samples of the meteorite. Each one was telling us a different part of the story of how the meteorite formed, in particular the temperatures and pressures under which it formed, which turned out to be temperatures around 100,000 times atmospheric pressure at around 1,500 degrees C or higher. And so now we knew they had to form under exotic conditions, not conditions that would be, anything that humans would have made naturally. Certainly not in Chicotka or anywhere. We also found other crystal grains in there. Other quasi-crystal phases in there. 2 other quasi-crystal phases in there. Not just one kind of quasi-crystal, but 2 others with different symmetries or compositions. So a total of 3 different quasi-crystals in one meteorite sample overall. And we found some unusual crystals, one of whom, behind my back, Luca had collaborated with other collaborators who have named in my honor. It's called Steinhardt. It's a crystal, but I've been mineralized officially as a result of this. There's only small samples of it left, which are barely visible to the eye, but I do have one of those samples as well. That could have been the end of the story. But then we decided, could we reproduce the conditions of 2 meteorite in space undergoing a collision and smashing together the raw materials to see if we could make a quasi-crystal that way? There's a group at Caltech led by Paul Asimov who does exactly those kinds of experiments using this camera. And essentially, the camera shoots a template at hypersonic speeds towards, well, the stack of materials you get to choose. The materials you might expect were the meteor that formed the quasicrystal. Could we make a quasicrystal that way? Yes. Right off the bat, we were able to make a quasicrystal that looked looked very much like the one that was in the meteor itself. In fact, this experiment's been repeated a number of times using different combinations of materials, and we find that we make quasicrystals at an incredibly high rate, which suggests there's something about shock pressures and having a mixture of 4 or more elements involved that leads to a high probability of quasicrystal formation. Something we have some ideas as to why that occurs, but we're not. It's still an open issue to try to understand at a basic theoretical level. But it tells us that quasicrystals are probably much less rare than we thought if you're willing to consider making them by other than standard synthetic means. And so that's an idea that we're still currently exploring. It also suggested other places to look for quasicrystals. Like, for example, there was an event that took place at 5:29 a.m., 5:29 Mountain War Time on July 16th, 1945. And some of you may recognize that time because it's pretty famous in history. It was the Trinity test in Alamogordo, New Mexico. Now, the Alamogordo test was done. That was the first implosion. That was the test of the first implosion bomb. Unlike the original atom bomb, it was an implosion bomb based on plutonium rather than uranium. So it had to be tested. We decided it had to be tested before it was used. What it did is it took the sand in the desert and it fused it to form a glassy-like rock, which is called trinitite. And if you go online, you can probably purchase trinitite. And when you purchase trinitite, you usually find that it's kind of a limesh green color. But it turned out that the interesting trinitite to study wasn't the limesh green stuff, but was kind of a reddish version of trinitite, an example of which you see here. Now, why is it reddish? Why isn't it lime green like the rest of the trinitite? Well, because it has copper in it. Where did copper come from? It was copper in the middle of the desert. Well, when they made the Trinity test, they had, no one wanted to stand by the bomb to drop it. So you had to communicate. And how do you communicate? With copper cables. So the copper cables. And when the bomb went off, it also fused the copper from the cables, in some cases with the sand, to make red trinitite. And that seemed to be the interesting candidate to look for, because I had a mixture of metals and other things that made for interesting combinations. And once again, the miracle man, Luca, found in one of these samples a grain which had a silicon, copper, calcium, iron combination which had never been studied before, which turned out to be a quasicrystal. In fact, these tests are continuing. I met this in the Alamogordo Desert, actually collecting sand from there. We're going to try to reproduce this experiment, not with atomic bomb, but with lasers to try to make a high pressure experiment to see if we can form it again. And then the most recent work that we're going to be doing is looking for quasicrystals in micrometeorites, stuff that's falling on the Earth constantly. For example, on the roofs of buildings. Here's a fellow, John Larson, who collects dust from the top of buildings and he isolates micrometeorites, and he finds all kinds of beautiful shapes, which are described in this book. And Luca and I were able to arrange to visit his collection recently. And in there, we haven't yet found quasicrystals, but we have managed to find examples of meteorites which have aluminum copper phases in it. Everything you need, not quite yet quasicrystal, but already the essential ingredients you need, in particular metallic aluminum and metallic copper together, the thing that was considered impossible before. We now have at least 5 different examples, both in Larson's collection and other collections, of that have this aluminum copper in them. I say us, but this is largely Luca's work. So what have we learned from all this so far? Well, I always had ambitions of what we would learn, and it's actually worked out better than I originally imagined. More successful. I mean, it's a pretty ambitious set of ideas for beginning. First of all, we've learned that quasi-crystals aren't as delicate as we thought. They can last a ability to survive in space, cosmic rays, and all kinds of other conditions, and still make it to Earth, land on Earth, and be recovered with still quasi-crystals. So the idea that they're delicate little things just ain't so. That's important for applications. That means you can use some quasi-crystals reliably. Second, you learn something from nature. That was on the other hope. Did nature teach us anything that would help us in the laboratory? Yes. Shock synthesis turns out to be a fruitful method for forming quasi-crystals not found by conventional laboratory methods. What else? Quasi-crystals are more ubiquitous than we thought. They've already been on Earth and we didn't know it. We didn't know they were there for the Alamogordo test. We've also found them in lightning strike sand and forms fulgurites. We found them in fulgurites. So obviously more ubiquitous than we thought, more robust than we thought. We've learned they're part of the primordial stuff that made up our solar system. There's nothing special about our solar system. If it's true in our solar system, it's going to be true in solar systems throughout the Milky Way. And as far as we know, solar systems throughout the universe. In fact, if you take a catalog of what the minerals would have existed before the Earth was formed, there's only about 60 of them that form the primordial minerals that form the planets. And now, among those 60 are 3 quasi-crystals that we didn't know, primal stuff. And it's probably, therefore, one of the most common materials in the universe, although you might have to go into space to find most of it. And so they probably exist in extrasolar regions throughout the universe, and their existence is telling us something about unusual processes that form them, but that's yet to be discovered. So this is not the end of the story, but I will end the talk here. Thank you.
Thanks a lot for this wonderful talk. It's really amazing what you achieved and the way you explained this to us. Thanks a lot. So I just put the light on. No. Okay. And time for questions. So I'm just going to ask the first question.
If you have an estimate, an idea of how big was the meteorite, the meteorite that hit the distribution, because what I found amazing is that this must have happened many years ago, and you can still find the grains of the original meteorite. Did I understood correctly?
Yeah, so the raw, not just the metal, but the other materials, those olivine dioxides are also date back. The olivine dioxides, the oxidated materials, not the metals, are very likely formed at the formation of the solar system, probably before the planets, or within a few 100 million years of the beginning of the solar system. The metals, we're still debating as to when they became part of the story. I still think the favorite idea is they form along with the other materials at the same time. So the quasi-crystals can easily date back to the very beginning of the solar system, when the sun first, matter first began to undergo nuclear reactions. But that's still a subject that we're investigating, so that's not a final conclusion.
So it came from the space.
It came from space, and we know something about when it landed on Earth, because we found it in clay. So there was a point in the Ice Age where this part of Russia was scraped clean, the surface was scraped clean by glaciers. And when they seeded around 15,000 years ago, then material became deposited. That deposit is rich in atomic material. You can use carbon dating to date it. And our quasi-crystals were found deep into that material. You can use that in touch. And that dates to around 10 to 15,000 years. So somewhere in that period is when we think Thanks for the question.
So other questions? Federico? Thank you again for this amazing lecture. I was just wondering, you have just presented the quasi-crystal with, let's say, 3D or let's say methods.
Yes.
I mean, is it by chance or is it possible to be expected such kind of quasi-crystal for lighter elements as well?
Well, first of all, the metallic bonds are as opposed to covalent bonds. There's no reason why they can't form covalent bonds. We do have examples of, we do have some examples that we know of where covalent bonds, but our search is definitely biased in looking for metals, because that made it easy to identify them. We're looking for something you wouldn't expect to see. If you see it, every time you see anything else like metallic aluminum, you go after it, because that might be a source. So we definitely, our search is definitely biased. But yeah, the quasi-crystals don't require. It's not required. Right. So in fact, if you're familiar, that recently there's a lot of interest in graphene, and particularly Moiré graphene. That's essentially a quasi-crystal. Right. So you can make it by layering crystals of various sorts. One second. We have students here.
Yeah.
We're going to be thinking about a question.
Very nice talk about something. Is it possible to have a quasi-crystal formed by molecular solids? So a crystal composed by molecule or mixture of molecules if one single molecule does not allow that?
So again, it's still early days, believe it or not, because most of the people who look at quasi-crystal are metallurgists because that's what the field is supposed to be. But there are things that, there are liquid, you can have something like similar to what you're talking about for the graphene. There are liquid crystal phases which also have rotation as you go from layer to layer, and that's a molecular liquid crystal, if you like, and which when you view along the perpendicular plane direction, you can view the projection as a quasi-crystal because they lock into certain units, not unlike the graphene case. So again, it's still early days because most of the people who work in the field don't try to make quasi-crystals out of molecules. There's some claims I've read that DNA also stacks in a way, like in a quasi-crystal, sort of a cadmium pattern. And I haven't been able to convince myself that that's a good example yet, but it's claimed.
Okay, thank you.
So we got a student question. Students sacrifice themselves.
Given the fact that the crystals are, let's say, believed to be stable at this point in time, do you foresee some sort of technological application for them?
That's a good question. So you've already had some applications. So the first, so some applications are that you might think of are very sensitive to high degree of perfection. Some are less requiring high degree of perfection. So those would be the first places to look. So one of the things that distinguishes crystal from quasi-crystal is that the motion of defects, like dislocations in crystals, which can move very easily in a crystal along with rows and columns, can't have no easy motion in a quasi-crystal, which means their elastic properties are different. So a quasi-crystal made of a certain set of elements, and a crystal made of nearly the same set of elements, crystal, will behave very differently elastically. You'll be able to bend one, and the other one will be harder and more difficult to bend. That's oriented to applications for certain industrial parts, where you want something hard, which you want something made of aluminum-based materials. Hypodermic needles would be another example. But I think the most exciting applications are yet to come. I think it's going to be as we're able to get more control on perfection, will be the quantum properties. We already have a hint of that in just what I was mentioning before. where these Moiré graphene samples would display superconductivity, whereas the individual graphene layer does not. So somehow quasi-crystallinity in this third dimension is enhancing superconductivity. And you can also make Moiré patterns out of quasi-crystal two-dimensional patterns. That's just something I'm working with a group trying to do right now. So that'll be a different kind of Moiré. A Moiré of a crystal on crystal is itself a crystal Moiré pattern. Quasi-crystal and quasi-crystal will be a Fibonacci Moiré pattern. And who knows what properties those are going to have, because you can only do it that way. So I think we're just at the beginning. It takes a long time before an idea, I mean, in spirit of materials, it takes a long time before you have a new material and it translates into an application for those purposes, because it takes so many steps along the way to turn it into something useful. But, but we're on that path. Thanks for the question.
Okay, one more question.
Sorry, you said that other two kind of quasi-crystal were discovered.
Yes.
I didn't remember the word like other two kind of phases or.
So we discovered two things. One, similar to the first one, but with a composition which was rather different, ratio of aluminum, copper, and iron than the first one. Separated enough that it's really effectively a different phase. The other example actually has a different symmetry. So the first two both have the symmetry of the icosahedral. The other one, the third one, has a different symmetry. It has planes of tenfold symmetry, which stack periodically in the third direction. So this is what we call a decagonal phase rather than an icosahedral phase. Those two have been discovered in the laboratory before, but now that too was found in nature along with these two icosahedral phases. So it's pretty amazing to find one, but to find three is really bizarre.
And the composition of these supercrystals are, I didn't get it, it's aluminum and copper. There are other elements.
I don't remember the catalyst, aluminum, nickel, nickel. Aluminum, nickel ion was the decagonal phase. The other icosahedral phase was like the first one, still aluminum, copper, and iron, but with different composition. It was rather different ratio, and it would make it distinct from the first one.
And for now, only three, those three kind of.
Those are the only three that we have found. We have found other aluminum, copper crystal phases in other micrometeorites. Actually, Lucas is leading this project. We found four others, but including four additional ones. So we're finding that aluminum copper was just a big thing that was making Glenn and Lincoln very nervous about this being real, and much of the community. We're finding this is now repeated. So now it's becoming familiar. And because now we know something we didn't know before, we know that these micrometeorites coming down from the sky that are on the moons themselves contain some of these phases. So suddenly, you don't have to go to Chukotka to find them. You can find them on the roof, maybe in your backyard, if you just collect enough of them.
So do you believe that knowing the process of formation, do you believe that other quasi-crystal types will be found?
I have to do that, yeah. Because we just started, so why should it stop? You can really find everything. There's nothing special. There's nothing special about them that would make them the only three. That's what I should say.
Thank you. You said that the quasi-crystals have also extraterrestrial origins. Does this suggest something new about the formation of the early solar system?
It does tell us that there's some source, something happened astrophysically that isn't included up to this point in the story of the formation of the solar system. So examples could be the early solar system. You could have had, it's been hypothesized, but never proven, there might have been lightning in the dust, in the cloud of dust to make a solar system. That can produce the kind of reducing phases you need to separate aluminum from oxygen. That could be the source. And so that would be, and how that would play a role is, since that hasn't been an accepted idea, how that would play a role in the whole story isn't yet found. More recently, there's a group that has been involved in that that's been hypothesizing the key was the formation of an early set of species of planet called urolites that might have had the right pressure conditions in the inside to produce these aluminum phases. Various processes, magnetic processes, other processes, to separate aluminum from oxygen, but then ended up colliding with other materials to form these phases. And that whole process is not part of the standard story either. So, yeah, when you discover a new process, you might get be surprised to find the overall story. One of the mysteries about our own Earth is what is the composition of the core of the Earth? We know it's iron, but it's not just iron. We know from various studies it's got to include metals other than iron, because iron's denser than we learned when we studied earthquake signals that pass through the core. And okay, maybe it's aluminum. Maybe there's a lot more of the stuff than we thought that formed the core of the Earth, thought to be centered of the Earth. So there are all these possibilities, just to throw things out there. Thank you.
So I don't know, I guess there will be many more questions, but I would leave the microphone to Luca for a couple of concluding remarks if you want, or for invite people you have been, you have been cited many times. You have a key role in this story, and I'm happy that all the things that you told us are really true. And we didn't know. And then after Luca's words, we have coffee break waiting for us upstairs, and I guess there will be more chances to interact with the board.
Well, actually, I have nothing to add because, in spite of the fact that I read the story, and it's always a pleasure to hear your lecture. So thank you very much to be here, and thank you.
Thank you.
We are all invited to join the lecture on Thursday in San Marco, so at 5 p.m.
It is on the Big Bang. Yes.
Sorry?
It is on the Big Bang. Yeah.
On the Big Bang, so Paul will be talking about universe, and then now you can join the conference and ask some questions. Thanks a lot.
That was so inspiring. I mean, apart from the scientific part, which I'm not familiar with, but the whole thought research is seriously impressive. How long did you guys stay?
20 years old.
Can I retrieve my USB? Can I retrieve my USB?
I don't need the USB. I need certain things back which are wrong.
It's this one. I think.
That's yours.